Okay. Okay, so today we will start the basic laws of circuit analysis, which are basically, as you can see here, Ohm's law. We talked about Ohm's law a little bit last time, and then something called KCL and KVL. For those who studied physics in high school, you might have heard these terms: Kirchhoff current law, Kirchhoff voltage law. But if you never heard these terms, don't worry about it. We will start from scratch. So there is no prerequisite for you that you need to know uh, any material before. Okay, so let's start with Ohm's law. Ohm's, of course, as most of the physics laws are named after certain physicists or mathematician. These are the most, I mean, these are the people who are came up with all these laws that we are. Most of the engineering is based on nowadays, and especially in this era, 1700, 1800. So Ohm's was a German professor, published a book in 1827, and he includes uh, what we call is as Ohm's law, as this is, you can say, this is the foundation of electrical engineering. It relates the most important quantities, which is the voltage and the current. Now we understand what is a voltage and what is a current. But for the voltage and the current to flow in the circuit, there is another element, which is the resistance. So the resistance, it controls the flow of the electrons. So if I apply a specific voltage, we don't change the voltage. If I increase the resistance, then I will reduce the current, and vice versa. And we can look to it in this nice comics. Uh, this is the amps trying to go through this pipe. This is the voltage. We said the voltage is a pressure. So the voltage is the one responsible to push the current to move in the circuit. Now, the resistance is the one that tries to hold the current, to control it, to reduce it. So if we have very high resistance in the circuit, then the flow of the current will be very, very little. And if we have a small resistance in the circuit, then this will allow the flow of the current. Okay, so resistors, this is how they look like. This is, I mean, resistors, they come up with different shapes, but this is the most common one. This is used in circuits, and in the kit that you will have resistors in that shape. And these colors that you see here, these are actually codes. So if you read them, then you can know the value of the resistance. You can Google that. This is not part of the course, but what I want to say, that these colors are not random colors. These colors represent the value, and when you read properly these strips, then you will be able to figure out the value of the resistance in ohms, in kilo ohms, in mega ohms, etc. Now, we know now two laws. We know that V is equal to I times R, and we know that the P is equal to V times I. These are the two relations that we know. So P is equal to V times I, V equal to I times R. Also, we know that G, the conductance, is basically 1 over R. Okay, so we can say that I is equal to V over R, or V times 1 over R, but 1 over R is G. G is the inverse of the resistance, so we said I is equal to G times V. Now, I can represent this relation in different ways, okay? So P is equal to V times I, and V is equal to I times R. So if I substitute the value of V here, then you can say that P is equal to, instead of V, will have I R times I, which is equal to I square R. So this is another relation of the power. or P is equal to VI, but we know that from Ohm's law that I is equal to V over R. So your P is equal to V times V over R, or equal to V square over R. So we have three equivalent laws to find the power, either P equal to VI, I square R, or V square over R. So it depends what do I have in my circuit. I will use the proper formula, but all of them will give me exactly the same answer. So let's see this simple um, example. For a resistor, and by the way, the resistance is given as such. This is the symbol of the resistance. So I have a resistance, its value is 40 kilo ohm, or it's equal to 40 times 10 to power 3 ohm. It's very important to watch this for kilo, for milli, because this can make a big difference when you do the multiplications or any calculations in your circuit. The current, is equal to 2 milliamp, or is equal to 2 times 10 to minus 3 amps. Now it's very good or very important to keep the SI units. The SI unit, this is a standard unit, uh, the current in amps and the resistance in ohms. So when you multiply ohm with amps, you get volt. Okay, so it's very good to write it in this format. So we want to find the voltage. We know that the voltage is nothing but I times R. This is the voltage. My I is equal to 2 times 10 to minus 3 times R, which is 40 times 10 to power 3. Now this will cancel with this, so this will give me 80, and the unit will be here volt. Why? Because this is in amp, this is in ohm. So if this is amp and this is ohm, this will be volt. So it's very important to keep the units in this basic thing. Okay, the power absorbed by the resistance. We said that the resistor only absorb power. They cannot produce power, they can only absorb power. And this power, this electrical energy, is converted into heat. So if you come and touch a wire, of course, insulated wire, please never touch a bare wire, because this you will be electrocuted. So if you have like a insulated wire, and usually there is a PVC material, plastic, rubber material around it, if you touch it, you will see there is a little bit of heat. How much current you have in your circuit, you have more and more heat. So the power, as we know, is equal to V times I. V, we know it, is equal to 80 volt times I is equal to 2 times 10 to minus 3. This is in volt, this is in amp, so the output will be in watt. So this is equal to 160 times 10 to minus 3 watt, or you can say this is equal to 160 milliwatt. Now, as I said, you can use different laws because we have all the quantity. We have the V, the I, and the R. So I can select any of the formulas, but let's just try to use all of them. P is equal to I squared times R. Your I is 2 times 10 to minus 3 square times R, which is 40 times 10 to power 3. So this is equal to 4 times 10 to minus 6, which is the I square, times 40 times 10 to power 3. So this will give me again 160 times 10 to minus 3 watt. 4 times 40 is 160. 10 to minus 6 times 10 to power 3 give you 10 to minus 3. Finally, also P is equal to V squared divided by R. And V here, your V voltage is 80 square divided by your R, which is 40 times 10 to power 3. And again, when you do this, this is equal to 160 times 10 to minus 3 watts. So any formula will give you the right amount of power. So this is the basics: power, voltage, current, resistance. These four quantities, you will be using them a lot in any circuit analysis. Now, let's start to see, okay, how I can analyze the circuit, how to find the voltages and the currents in the circuits. Okay, start with some definitions. Conductors. An ideal conductor has no voltage drop across the end. Now, we know that the voltage is equal to I times R. Now, an ideal conductor means that your R is equal to 0. Hence, the voltage is equal to 0. So there is no voltage across a conductor. Whenever a current goes through the conductor, there is no voltage drop that. Okay, so if I have 2 points in a circuit, and if I short them like this, then they become the same point. And I will come to this into details. So these are very, very important definitions we need to understand. Node, branch, and the loop. And here we'll give some example. A branch represents a single element, such as a voltage source that either independent or dependent voltage source. This is considered as a branch. A current source is considered a branch. A resistance is considered as a branch. So any of these elements in the circuit is in a branch. So for example, this circuit have 1, 2, 3, 4, 5 branches. So these are a branch. A node is the point that connects between 2 or more branches. So these branches are connected together by a node. So for example, this 5 ohm, this 2 ohm, this 3 ohm, this 2 amp current source, all of them connected to one node. All of this is one node. How do I know? Because between this point and this point, there is no any branch, or there is no any other element. Between this point and this point, there is nothing. So you can look to it all of this as one point. Between the voltage source and the 5 ohm resistance is also another node here, which is this point. At the bottom, all of these branches, the 2 amps, the 3 ohm, the 2 ohm, and the 10 volt, all of them connected to one point or one node. As you can see here, there is nothing between this point and this point, or between, when I say nothing, means there is no branch or there is no element. Hence, all of these points are considered as only one point. Finally, a loop. A loop is any closed path in the circuit. So if you start a certain point and you went through one closed loop and you come back to the same point, this is considered as a loop. For example, you start here, you go all the way, come back. So this is considered as a loop. Also, this is a loop. This is a loop. The big one is another loop. So any closed path, so it could be one loop or combination of loops within that big loop, is considered as a loop. So keep this in mind. What is a branch? What is a node? What is a loop? This is very, very important when you analyze your circuit. Now, let's start trying to trigger you guys. Uh, let's see here. What were we talking about that we will be using over the course of the term? We're talking about the basic laws of electricity. Now, let me ask you this, our first bonus question of today. How many nodes and branches we have in this circuit? So please write down the nodes and the branches. Okay. Oh, too fast for me to catch the answers. Let me see here. Let's see if there's anyone got the right answer. So far, I didn't see any right answer, to be honest with you. Let me see here. Let me see. I'm just scrolling down. So far, no one got the right answer. Oh my God. You have everything. You have every number in the world except the right ones. Okay, finally. We have Elise and Angela. Yeah, hopefully I'm saying it right. Elise. Elise or Elise or Elise. I don't know how to say it honestly, but Angela is the one that got the right answer. Okay, so what is the right answer? Let's see. Let's count the branches. Branches simple. So please, Elise, send to me your ID. So this is one branch, two, three, 4, 5, 6, 7. So many of you get that right. So 7 branches. Branch is simple, the number of elements. Now the nodes is the tricky ones. Okay. So this, some of you give too many nodes. They count everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I get some people get 10. No, it's not. This and this are the same point. Why? How do I know? Because there is nothing in between. There is no branch between. So this and this will be all the same point. This is 1. Will this and this be the same point? No. Why? Because we have 5 ohm in between. So this is a different point. But how about this and this? They are the same. This and this, they are the same. So all of this is another node. This is called a node. This is number 2. Then this and this and this and this, all of this is just one node. Why? Because the nothing in between them, nothing between this point and this point and this point and this point. There's no any other branch. So this is number 3. Now, where most of you now did not pay attention to is this node. This is another node. Why? Because this connect between this branch and this branch. So you will have here basically 7 branches and 4 nodes. This is the right answer. Okay, let's move on. This is very important here because you cannot apply the KCL and the KVL until you understand what is a node. If you don't know what is a node, then you will have a problem to do that. Okay, I have a question here. Someone says, why this is a node? Number 4. What is a node? What is the definition of a node? The node is a point of connection between 2 or more branches. What is a branch? A branch is an element. So the 2 ohm is an element. The 13.7 amp current source is another element. Then this is the point of connection between 2. Then this is a node. Okay, please guys, don't let me leave this slide until you understand what I have done here, because everything will be built. I mean, you will see that this circuit course is like you are building a structure like in civil engineering. So we build it brick by brick. So now we are laying down the foundation. These are the foundations. Without the foundations, you will be shaky. Your building will be shaky. You will not be able to grasp some advanced topics in the future. Okay, now let's start with the real deal here. We'll start with Kirchhoff laws. And these are the fundamental laws of electrical engineering. Kirchhoff is a Russian, and when he was a student, he came up with these techniques. Uh, and he came up with 2 laws, and they are named after him: Kirchhoff current law and Kirchhoff voltage law. He wanted to come up with something uh, easier to analyze the circuit. Then he came up with these 2 laws. Let me, before move on. Let me see if there's any other questions here. If we were to simplify the previous circuit diagram into nodes and branches, how could we do that? What do you mean by the previous circuit diagram? What do you mean by simplify? We don't simplify the circuit. We just count. We do not simplify it. We will learn later on how to simplify the circuit when we add the elements together. But we would cover that later on. Okay, so let's see what is these laws. The first one is the Kirchhoff current law, which we will cover today with some examples. The Kirchhoff current law, this is related to current. So the law itself is about currents in the circuit. That states that the algebraic sum of currents entering a node is 0. And note here the algebraic sum. So it means that current enter the node will have a different sign than the current leaves the node. So if we assume a current enter the node is positive, so the current leaves the node will be negative. And vice versa. It doesn't really matter. You can assume whatever you want. Or you can say that summation of current enter the node equal to summation of current leaves the node. So both will end up having the same thing. So for example, let's look here. This is my node, and we have these currents. So I can use the first definition, and we get exactly the same relation. So let's assume currents. Let's assume that if we have I enter, then it is positive. I leave is negative. This is my convention. Or you can do it the other way around. It doesn't really matter. So we have here current enters I1, I2 leaves minus I2, I3 enters plus I3, I4 enter plus I4, I5 leaves minus I5 equal to 0. So this is one way of looking into it. Other way is say that the current enter the nodes equal to the current leaves the node. So I1 enters, I2 leaves, I3 enters, so plus I3, I4 enters, so plus I4, I5 leaves plus I5. So if you look to this equation and this equation, they are identical. I1 plus I3 plus I4 equal to I2 plus I5. If I take this to the other side, I will have this. Or if I take the I2 and the I5 to the other side, I'll get this equation. So both ways are correct. It depends which one you are more comfortable. You can say either summation of the algebraic summation of the currents is equal to 0, or current enter the node equal to current leaves the node. Both will give you exactly the same thing. So when you look here, this I1 enters, I2 enters, I3 leaves. So you say I1 plus I2 minus I3 is equal to 0. Now here, I change the convention. So I made the current enter the node is minus. The current leaves is positive. But it doesn't really matter. If I say I3 minus I4 equal to 0, or if I say minus I3 plus I4 equal to 0, in both cases, I3 is equal to I4. Current enters equal to current leaves. So it doesn't really matter how I can uh, express, but you have to be consistent. In any node, you have to be consistent. If you assume that the current enter the node is positive, then every single current that enter the node will be positive. And every single current has to be leaving the node has to be negative. So you need to be consistent. This is the only thing that you need to pay attention to. So let's look here and let's find IA. What is IA? What is IB? And here, what is IC? Let me give this as a bonus to you guys. Let's see how much you can get here. IA, IB, and give me the three currents. Give me all of them in one line. IA, IB, and IC. All of them. I think we have a winner here. We have a winner. Yes. The winner is Dayong. Dayong Ju. Dayong Ju. Yes. Okay, let's see. So now we have two winners. Please, after the class, send me your ID to give you the 0.5 bonus. So let's look here. This current enters. So I can stick to anything. So let's see the first example here. Okay. So 1 amps enter. So this is 1. 3 enters plus 3. IA leaves minus IA equal to 0. So from this, your IA will equal to 4. So this is 4 amps. Let's see this one. Now, these two are the same node. There is nothing here in between. So these two are exactly the same node. So 3 enters plus 1 enters plus IB enters, but 2 is leaving, minus 2 equal to 0. 4 minus 2 is plus 2 with other side, so your IB equal to minus 2. So this is minus 2 amps. Finally here. So we have 1 enters plus IC enters plus 4 enters plus 3 enters equal to 0. 1 plus 4 plus 3, 8. Take it to the other side. So your IC is equal to minus 8 amps. And this is minus 8 amps. Okay, so this is how you solve this question. Now let's put things into a perspective of a circuit. Now let's put everything into a circuit. And here it says find I1. Could you please go back? Okay, I will go back. Let me see if you guys have any question here. Okay, Ali, do you have any question? Okay, no problem. So let's see this. Now this is what you expect to see. You expect to see a circuit now. Okay, and now the currents are given to you in some branches. For example, I know the current through this branch. I know the current in this branch. Okay, this through this and this. But I don't know the current here, I1. I know the current here. I don't know the current there. Okay, so if we look to node A, this is this node. This node is what is basically, it is this point and this point and this point, because there is nothing here. So all of this is basically one node. All of this is just one node. Now, this node has how many branches connected to it? We have this, one, two, three, and four. So it's good to count how many branches connected to that node. Why? Because you will know how many elements in your equations has to be there. So I1 enters, this 12 milliamps leaves the node. So this becomes minus 12 milliamps. 2 enters, so plus 2 milliamp. 4 enters, plus 4 milliamps. That's it. We have 1, 2, 3, 4 currents equal to 0. Summation of the algebraic summation of all currents equal to 0. So this is equal to I1 minus 6 milliamp equal to 0. So from this, your I1 will equal to 6 milliamp. Let me see if you have any questions here. Why does the node not go all the way the right bottom? Oh, okay. Okay. It doesn't matter. I can, it doesn't really matter here because I already connect to this branch. It is actually the way all the way here. The node can go here, but it does not affect anything because this current is the same as this current because the current goes here and there. Okay, so 2 milliamps. Okay, let's see if I have any other questions. Why it is minus 12 instead of plus 12? Because we have a convention. Current enter the node is positive, current leaves the node is negative. That is the convention we established. We could establish any other convention. We could say current enter the node is negative, current leaves the node is positive, or current enter the node equal current leaves the node. Any of these three conventions will give you exactly the same answer. So here I1 enters the node, it's positive. Okay, but this 12 leaves the node. It's going away from the node. It's not going towards the node, so this becomes negative. This 2 amps is going to the nodes. This 4 milliamps going towards the nodes, so these are positive, and this is the only one is negative because it's going away from the node. Hopefully that's clarify things. Okay, now let's look here. Now it's things start to getting harder and harder. Okay, so here we want to find I0 and I1. Okay, so what is I0 and what is I1? Where is I0? This is I0, this current. Okay, so this current. Now this current will be the same current until it reaches to the node. So I0 will be, this here will be I0. Here will be also I0. All this is the same current. But once it starts to reach a node, then it will branch out or branch in. It will be different. So in this whole thing, as far as there is no node that distribute the current, then the current will be the same. Okay. Now this current, for example, this 4 milliamps is the same here. This is 4 milliamps. But here, this is 5 milliamps. Okay. So now let's find my I0 and my I1. Let me apply KCL at node number 1. And here we learn something that sometimes we need to add a variable to my circuit, because here I have 4, I have 2, but I don't know what is this current. This is not given to me, so I will identify this current. I will call this is current, this IA. Okay, so we have 2 enters the node, so we have plus 2 milliamps. 4 also enter the nodes, then plus 4 milliamps. IA now leaves the node. So IA will be minus IA. That's it. We have 1, 2, 3 branches connected to this. Then this is equal to 0. So 2 plus 4 is 6. So then your IA is equal to 6 milliamps. So now this current that enters here is equal to 6 milliamps. Now apply KCL at node number. It's very important to number the nodes so that your answer is clear to us. When we grade your answer, we understand what we are talking about here. So KCL at node number 1. So you are referring this, you number this as number 1. So your answer is neat. We understand what exactly you are doing here. You don't just write an equation without referring to what exactly you are doing here. Okay, so again, this current enters the 6 milliamps, so this is plus 6 milliamps. This leaves, then this is minus 3 milliamps. This is leaves, this is your I0 now. This is the first unknown that you want to find. Minus I0 equal to 0. 6 minus 3, this is 3 milliamps. And this is equal to I0. So your I0 here this current that enters here is equal to 3 milliamps. Okay, finally, KCL at node number 3, which is this one. Now, this 3 enters the node, so plus 3 milliamps. This is enters, and this is leaves the node, so minus I1, and this leaves the node minus 5 milliamp equal to 0. Okay, so 3 minus 5 is minus 2 milliamp equal to I1, and this is your I1. Now, when we say I1 is equal to minus 2 milliamps with this direction, if I1 is in this direction, it will become equal to 2 milliamps. So we said that when we reverse the current direction, we will get the positive. Do I need to reverse the current? No, we don't need to do anything. Okay, if we say I1 equal to minus 2 milliamp, it is understood that the I1 is equal to 2 milliamp in the reverse direction. Okay, so this is the full solution here. Okay, now we will just introduce to you the Kirchhoff voltage law. So the Kirchhoff current law deals with nodes. The Kirchhoff voltage law deals with loops. Okay, so it says here that the algebraic sum of all voltages around a closed path or a loop is 0. So if we add all these voltages around one closed loop is equal to 0. Now we have one question. The first question we have, why this polarity given as such? We will talk about that in Thursday. How we can assign the polarity based on what? But now let's assume that we already know the polarity here. Okay, same as the current direction. How do I assign the current direction in the circuit? Why in this circuit we assume the current going this way, not that way? Okay, so again, this will be discussed on Thursday when we put everything in one context to deal with the KCL and the KVL at the same time. So basically here you assume that you stand up here. This is your starting point, and you want to take a walk around this loop. So you'll go, and as you move, you will write down the first sign of the two polarities, because every voltage has two polarities. So the first one you will see as you walk, this is the sign that you will write down. So if you walk this way, you see plus here. So this becomes plus V2. Then you pass V2 and you come here. Then you see plus V3. Move on, keep on. You come here, you see minus V4. Keep on. Plus V5. Still. Minus V1. Then you come back to your point of origin equal to 0. So this is summation of all voltages around a closed loop is equal to 0. That is the Kirchhoff voltage law. Okay? Any question here? Let me see if you have any question. Okay, I don't think so. There's any question here. Okay, so let's give this example, and then this is the end of today's lecture. It says here find VBC and VAC here. Okay. Okay, so you are here, and you want to add all the voltages here around you. Okay, so we have 4 plus 4 volt plus. Now, this is, let's remind ourselves, this is a dependent voltage source, or we call it voltage controlled voltage source, because it's a voltage source. How do I know that? Because plus minus. How do you know it's a dependent voltage source? Because of the shape of the source. It's a diamond shape. It's not a circle shape. How do I know this is a voltage dependent? Because its value depends on another voltage. Okay, so this is plus 3Vx, which is the voltage, plus Vx, then minus 12 equal to 0. So we have 4 minus 12, this is minus 8, this is plus 4Vx equal to 0, or your Vx is equal to 2 volts. This is your Vx. This is your variable. Now, I want to find the voltage VBC, the voltage between B and C. The voltage between B and C is the 3Vx. Okay, but the 3Vx, we know the Vx, this is equal to 3 times 2, which is equal to 6 volt. Then it says VAC, the voltage between this point to that point. So it is a summation of this voltage and this voltage. So this is equal to plus 4 plus 3Vx, which is equal to 4 plus 6 equal to 10 volt. Okay, let me see if you have any question here, because this is the last thing I would cover. Okay, this is a very good question. What if I went the other way around? Okay, I didn't go this way, I went this way. Let's see what will happen. Okay, so let me clean up this. Okay, let me clean up everything and let me go this way. So we have here plus 12, then go all the way minus Vx minus 3Vx minus 4 equal to 0. So we have 12 minus 4 is plus 8 minus 4Vx equal to 0. So from this, your Vx is equal to 2 volt, which is exactly the same as the previous one. So same to what we mentioned about the KCL, it doesn't really matter. You can go, you assume current enter is positive or equal to negative. As far as you stick to this convention, same thing in the loop. You can go to the clockwise or anti-clockwise. It doesn't really matter as far as you keep on when you following the polarity. This is plus minus, so this is plus 12. If you went the other way around, it becomes minus 12. So if you are consistent with this, it doesn't really matter the direction you will choose. I will stop here. I think we have good material to grasp. And then on Thursday, what we will be doing, we will be studying more about this. We will have more examples. And one thing here I'd like to keep in your mind is the following, that you cannot solve the circuit, almost any circuit, unless you use the 3 laws, KCL, KVL, and Ohm's law. So far, we are using one at a time. In the beginning, we used only Ohm's law. Second, we used only KCL. And then now we are using only KVL. But in practical circuits, and we'll see why on Thursday, you need the three of them to be together, and that will be the main topic that we will be covering on Thursday when we put everything together. And by the way, KCL, KVL, Ohm's law, this will be your first one of the, I mean, this will be one of the questions in the midterm, definitely. So it's a very important topic, and the tutorial that you have is also for KCL and KVL as well. Okay. If you have no further questions, then have a nice week, and talk to you on Thursday. Bye, everyone.